This video is about logarithmic functions. This is AP Precalculus topic 2.11. If you appreciate this content, please give it a like. Write limit statements for the end behavior of the following logarithmic functions. We need to start by sketching a graph for number 1. For logarithmic functions, the y-axis is the asymptote. When the a value is positive, it's going to be increasing like this. So that's the way the graph will look. Let's do the left end behavior first. It will not be the limit as x approaches negative infinity. Because of the asymptote, this curve does not go past the y-axis. So we will have to say the limit as x approaches 0 from the right instead of f of x equals. As we go towards the left, as we approach 0 from the right, f of x is approaching negative infinity. So that's the limit. The right end behavior, as usual, is the limit as x approaches positive infinity of f of x. As we go towards the right, the function is rising. So this limit is positive infinity. For number 2, the a value is negative. So compared to the parent function, this graph will be reflected over the x-axis. The y-axis is still an asymptote, but it will be decreasing like this. The left end behavior will be the limit as x approaches 0 from the right of g of x. As we approach 0 from the right, g of x is approaching positive infinity. So that's the limit. The right end behavior will be the limit as x approaches positive infinity as usual. As x approaches positive infinity, as we go towards the right, g of x is falling, approaching negative infinity. For number 3, it does not matter that this a value is less than 1. It's still positive, so the graph will still look like this. So this is going to have the same end behavior as number 1. The limit as x approaches 0 from the right of h of x is negative infinity. As we approach 0 from the right, h of x is falling. And the limit as x approaches positive infinity of h of x is equal to positive infinity. As we go towards the right, h of x is rising. The graphs of k and m are shown below. Use the graphs to answer the following. Number 4, is the graph of k increasing at an increasing rate, increasing at a decreasing rate, decreasing at an increasing rate, or decreasing at a decreasing rate? From left to right, k of x is obviously falling, so it is definitely decreasing. So the answer is not going to be A or B. But is the rate increasing or decreasing? One way to answer this question is to remember the graphical relationships between f, the rate of change of f, and the rate of change of the rate of change. This comes up a ton in calculus, so this is worth memorizing. Pause the screen, take notes, practice. You should be able to write this on a piece of scratch paper before your next test. The part that's relevant to this question is the part that says, if the original function is concave up, the rate of change is increasing. If f is concave down, the rate of change is decreasing. We can see that k of x is concave up. So therefore, the rate is increasing. That means the answer is C. Here's another way to think about it. On a graph, rate is the same thing as slope. So if the slopes are increasing, then the rate will be increasing. If the slopes are decreasing, then the rate is decreasing. So what's happening with the slopes? On the left, it starts out very steep but negative. So it starts off very negative. So the slopes over here in this area are like let's say -4. And then it gets a little less steep in this area. Let's estimate -2. And then somewhere in here we have like a 45-degree tangent line. This would be a slope of -1. And then later it gets less steep, so that would be like -1/2. So as we go from 4 to -2 to -1 to -1/2, these values are getting less negative. On a number line, we'd be going to the right. So these slopes are increasing, therefore the rate is increasing. So that's another way to realize that the answer is C. For number 5, we need to match the end behavior to this graph. On the left, k of x is rising. It is approaching positive infinity. On the right, k of x is falling. It is approaching negative infinity. So we just need to look for the option that says positive infinity for the left end behavior and then negative infinity for the right end behavior. They all correctly say the limit as x approaches 0 from the right, so that's something to watch out for. But we just need the one that says positive infinity on the left and negative infinity on the right. So the answer is C. Number 6, which of the following could be the equation for k? Notice that this is one of the decreasing versions of a logarithmic function. So the a value is going to have to be negative when it looks like this. A positive a value for a log function looks like this. So it's going to be a negative a value, so we've narrowed it down to either a or c. It cannot be b or d. I just realized that option C is not even a log function. So C can't be the answer. The answer is A. We can tell this is a logarithmic function because we have a vertical asymptote. The y-axis is the asymptote. That means log function. If it was going to be exponential, like C or D, then the x-axis would be the asymptote, like one of these or one of these. So the answer is A. Number 7, which of the following equations could be k inverse? The inverse of a log function is an exponential function. So for starters, we're looking for only exponential functions. So it's not going to be C or D. I think the easiest way to choose between A and B is to make a quick sketch of the reflection of this over the line y equals x. Let's sketch the exponential function that corresponds with this. Here's the line y equals x. This little tail right here that is approaching the y-axis will reflect over this line and instead will be approaching the x-axis. So that tells me that the general look of the curve will be something like this. It's still going to, it's going to hit the point 0, 1. Like say if this is the point 1, 0, the y-intercept will be the point 0, 1. So I'm going to hit this point, but then I'm going to make this little tail approaching the x-axis instead of the y-axis. So this green curve shows what the reflection would look like. This shows roughly what k inverse is going to look like. Notice that k inverse is above the x-axis. That tells us that the a value is going to be positive. So that eliminates b that has this negative in the front. So right there, that tells me that the answer is A. I also knew that this b value had to be between 0 and 1 because of the way that the exponential curve is getting closer to the x-axis. So A makes sense for that reason as well. Now let's switch to the graph of m of x and answer all of those same questions. So is the graph of m increasing or decreasing, and is the rate increasing or decreasing? From left to right, m of x is rising. So we know that m is increasing. So it's not going to be C or D. What about the rate? The quickest thing to do is to go by concavity, like I mentioned before. This curve is concave down, which tells us that we are talking about a decreasing rate. So that's the fastest way to realize that B is the answer. The other way to think about it is to imagine little slope segments going from left to right, and then give them estimates. Like this one is very steep, so this would be +4, and this would be a little less, +2. This is a little less steep, +1. Less steep still, +1/2. From 4 to 2 to 1 to 1/2, these slopes are decreasing. Therefore, the rates are decreasing. Number 9, which of the following pairs of limit statements correctly describes the end behavior of m? On the left, m of x is approaching -infinity. On the right, m of x is approaching +infinity, falling on the left, rising on the right. Let's make sure that they all say x is approaching 0 from the right, so that part is correct. So we just need to look for -infinity on the left and +infinity on the right. See, negative, 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 positive. The answer is B. Number 10, which of the following could be the equation for m? This is clearly a logarithmic function because the y-axis is the asymptote. So we can eliminate C and D immediately. Notice that both of the remaining options have a b value of 8, which is greater than 1. As long as that b value is bigger than 1, we can easily tell whether the a value will be negative or positive, because if the curve is increasing, the a value is going to be positive in this case. When the b value is bigger than 1 and the a value is negative, then that's when it's going to be decreasing. So the fact that this is increasing like this tells me that the a value is positive, and the answer is B. Alright, by far it's most common that we are going to see a b value that is bigger than 1. When we run into a problem that's like log base 1/2, it's a little bit more tricky, and we will cross that bridge when we come to it. Number 11, which of the following equations could be m inverse? Let's reflect this graph over the line y equals x to find the graph of m inverse. Here is the line y equals x. This point right here is the point 1, 0. So this will end up right here. Alright, I'm just reflecting diagonally across the line. So my y-intercept will be here. This tail that is approaching the negative y-axis will now be approaching the negative x-axis, because the x-axis is now the asymptote. That means the curve is going to look something like schma. This is an exponential function. So we are looking for an exponential function. So this one that says log in it, that's definitely not going to be the answer. Notice that the graph ends up above the x-axis. For an exponential function, that's how we know that the a value will be positive. So we will throw out b, which has a negative a value. For exponential functions, this b value is what tells you if the curve will be increasing or decreasing, like that. Because this curve is increasing, that tells us that the b value must be greater than 1. So we will pick the version that has a b value greater than 1, and the answer is C. Selected values of several logarithmic functions are shown in the tables below. For each table, find the value of the constant k. For logarithmic functions, we need the output values to be equally spaced. For number 12, they are. Now we look for a common ratio among the input values. It'll be easiest to see right here. 30 divided by 3 is 10. So this is times 10. 3 divided by 0.3 is also 10. So clearly the common ratio is 10. We can use that common ratio to find the value of k. If we multiply by 10 again, 30 times 10 is 300, so k is equal to 300. Number 13. First verify that the output values are equally spaced, and they are. Now let's find the common ratio among the input values. So this is a little awkward, but we need to divide each input value by the previous input value. So I'm going to do a little scratch paper work here. I need to do 3 divided by 3/4. But we know that when you divide by a fraction, you multiply by the reciprocal. So this is the same thing as 3 times 4 over 3. The 3's cancel out and you simply get 4. So the ratio here is 4. Applying that ratio again, 3 times 4 is 12. So k is going to equal 12. We can check our answer by following through. Should have done this on the last problem. But if we follow through and apply the common ratio again, let's make sure that we are getting 48. So k is 12 now. 12 times 4 is 48. So k is definitely the answer. Looking back at number 12, let's check our answer on this one as well. If we multiply by 10 again, so remember k was 300, and 10 times 300 is 3,000. So that one checks out as well. Number 14, these output values are looking a little bit weird with all these k's floating around. However, we can still tell that the output values are equally spaced because from k to k plus 1, k plus 1 to k plus 2, we are still increasing by 1 each time. So output values equally spaced, check. Now let us look for the common ratio among the input values. Dividing 6k by 12k, that is 1/2. So the ratio here is 1/2. We have another pair to look at. 6 to 3, this is also going to be times 1/2, etc. We can work backwards from these last two numbers to figure out the value of k. So working in the reverse, we are doubling each of these numbers. So 3 times 2 is 6. 6 times 2 is 12. So we know that 3k must equal 12. Let me write that a little bigger. So 3k must be 12. Dividing by 3, that tells us that k is equal to 4. Number 15, first verify that the output values are equally spaced. Now we are ready to look for the common ratio among the input values. So dividing each term by the previous term. So let's start down here where the numbers are clear. 3 divided by 27. 3 goes into 27 9 times. So this reduces down to 1/9. So this is going to be times 1/9. Let's just make sure that we get 1/9 by looking at one more pair. Let's use the first pair. If we divide 3 to the 5th power divided by 3 to the 7th power, will we get 1/9 again? That will convince me that this is truly the common ratio. Well, when you divide with like bases, you subtract the exponents. 5 minus 7 is -2. So this would be 3 to the -2 power. This drops you down to the denominator. This is 1 over 3 squared, which is 1/9. So clearly the common ratio is 1/9. So applying the common ratio one more time, let me clean this up. To find the value of k, we need to apply the common ratio one more time. In other words, we need to multiply 3 times 1/9. Well, so k is going to equal 3 times 1/9. That is 3 over 9, which simplifies down to 1/3. Number 16, let f of x equal 3 log base 5 of x plus 4. Part A, find the domain and range of the function f. Let's draw a quick sketch. This is a log function, so it has a vertical asymptote. If we didn't have the plus 4 here, the y-axis would be the vertical asymptote, and the fact that the a value is positive means that we're going to have the increasing version of the function, which would look like this. However, having the plus 4, this is a translation by -4. In other words, the graph that I just drew will be shifted to the left by 4. That includes the vertical asymptote. The vertical asymptote will be at x equals -4, and the curve will look like this. The range of a log function is always from -infinity to +infinity, but the domain is dictated by that vertical asymptote. So the domain in this case is from -4 to infinity. I'm going to write this in interval notation, so we will say -4 to infinity. Make sure you use a parenthesis on the -4. The curve never reaches the vertical asymptote, so -4 itself is not part of the domain, and we show that with a parenthesis instead of a bracket. As I mentioned, the range for a logarithmic function is always -infinity to +infinity, because the y values go down forever and up forever. Part B, if g of x equals -2 times f of x minus 3, find the domain and range of g. So g of x is just a transformation of the original function f. So we are doing a reflection over the x-axis, there's a vertical dilation, and there is a horizontal translation by 3 of this log function. So we're flipping this around and moving it around, but it's still a logarithmic equation. So the range is still going to be -infinity to +infinity. That's not going to change. We just need to focus on the domain. And the domain is going to be dictated by the vertical asymptote. So f of x has the vertical asymptote at -4. All we really have to worry about is what's happening here on the inside. And all we see is a horizontal translation by +3. Let me write that down. That means to the right 3. If we take -4 and we move to the right 3, in other words, we add 3, we will land at -1. So for function g, the vertical asymptote will be at -1. So the domain will be from -1 to infinity. As long as there's no reflection over the y-axis, we don't have to do anything else. And we don't see any multiplication inside of the parentheses, so there's no reflection over the y-axis. So it's still facing to the right, so it's still -1 to infinity. Part C, k of x is f of 2x plus 7. Find the domain and range. A horizontal dilation and a vertical translation of a logarithmic function is still a logarithmic function. So the range will still be -infinity to +infinity. Notice that there is no negative on the inside of the parentheses. So there's no reflection over the y-axis. The curve will still be facing towards the right. So the domain will depend on what the vertical asymptote is. This 2 on the inside is a horizontal dilation by a factor of 1/2. This will affect x values, including the x value of the vertical asymptote. So any x value that was -4 will be multiplied by 1/2. So the new x value will be -2. This will be the new location of the vertical asymptote. So therefore, the domain will now be from -2 to infinity. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.